Is AI truly creative, or are the current models just mixing up and reproducing what they've been trained on? This question is currently super controversial. Linguist Noam Chomsky has bluntly described ChatGPT as basically high-tech plagiarism. But Sam Altman from OpenAI, not so surprisingly, has a different perspective. He agrees with David Deutsch that creativity is just taking something you saw before and modifying it a little, and on this count even the current models are truly creative. Then there was this stunning study. The authors looked at diffusion models that are widely used now for image creation. Diffusion models are deep neural networks like large language models, so they get trained on lots of data to learn from it. However, they process input differently. They start from pure noise and iteratively denoise it to create images. In this process, they draw on the data that they've been trained on. In this new paper now, the authors show that this image creation is actually highly predictable. They used examples of small images and showed that, given the random seed and access to the training images, they can predict the final image extremely well without any deep neural net or training or anything. I find this amazing. All this talk about emergence in neural nets, and then the result is that predictable. Now, let me be clear that the existing image generation models are dramatically more complicated than what they tested in the paper, but I think it gives us a big clue to the origin of the supposed creativity of AI, and also why it's often lacking. But maybe I'm odd for finding that AI output lacks creativity. Because somewhat distressingly, there have been multiple studies showing that humans rate AI-generated ideas as more creative than human-generated ones. This has been shown for tasks like essay writing, gift ideas, but also brainstorming alternative uses for everyday objects and so on. The authors of the latter paper concluded rather unflatteringly that AI language models demonstrate higher creative potential than human respondents. And that was last year. Then again, if you look at the details, things aren't as clear-cut, because large language models don't excel uniformly on all creative dimensions. One recent study, for example, evaluated several models on multiple criteria, such as the quantity of ideas, the variety, originality, and elaboration. They again used tasks such as finding surprising uses for everyday items or imagining what one would do in an uncommon situation. They found that large language models are especially good at elaboration, but often fall short on originality. That is, they can produce detailed, well-developed ideas quickly and in high number, but they often repeat and recycle. That said, in a certain twist of irony, the authors used GPT to rate the creativity of the responses. They also paid 20 humans to rate a subset of answers, and they say the human ratings are moderately correlated with the AI ratings, though possibly the humans used AI for their rating, so honestly I'm not sure who's rating what here. But let's move on. As another study documents, a big part of the reason that AI seems more creative is that it generates new ideas faster. That is, in creativity tests, humans are at a disadvantage just because we think much more slowly than microchips. Indeed, a paper which claimed that AI can handle creative tasks also found that when questioned 10 times, an LLM's collective creativity is equivalent to 8 to 10 humans. That's unfair! I can't compete with 10 others. So now what? Is AI creative or not? Well, maybe both. A team of computer scientists recently proposed that we should distinguish the easy problem of machine creativity from the hard one. The easy problem is getting AI to generate art or writing that looks creative to us, which even the current models can do. The hard problem is deeper. Can an AI ever be creative on its own, giving rise to genuinely new ideas rather than just, as Chomsky put it, engaging in high-tech plagiarism? Though I think they've missed a relevant point there, which is that AI ideas look creative to us now. But the novelty is wearing off quickly. A year ago, people were amazed by AI-generated poems. Now we just scroll past them and get to the AI-generated thumbnail of a fake podcast between Einstein and Napoleon. You probably expect me to end with some intelligent conclusion, but really I don't have one. On the one hand, I agree with Sam Altman and David Deutsch that there's no magic in creativity, it's just modifications on what you've seen before, and there's no reason why machines can't be creative. On the other hand, I'm personally constantly underwhelmed by the lack of originality in the systems I'm using. So what do you think about this? Leave me a note in the comments while I'm busy blocking the AI bots. Einstein was wrong again about quantum mechanics because of something that physicists measured at MIT. Maybe you've seen the headlines last week. They go back to a press release. As you know, I'm a great defender of Albert Einstein, who didn't say half the shit people say he did, so let's have a look. This recent episode of Einstein Was Wrong was brought to you by the famous Bohr-Einstein debate at the 1927 Solvay Conference. Einstein was convinced that something was fishy about quantum mechanics, and he'd been trying to poke holes into it for some while. If he were alive today, he'd probably be running a YouTube channel called Quantum Nonsense Debunked. In this case, he didn't believe that the properties of particles can just not be determined. By this I mean that in quantum physics, a particle that has a definite position just doesn't have a definite momentum. But in 1927, Einstein argued that this isn't right. For that, he used a thought experiment that's a variant of the double-slit experiment. Imagine you send photons, the quanta of light, through a plate with two small slits, that's the double slit. You'll see an interference pattern, but only so long as you don't know which slit the particle went through, according to quantum mechanics. Nonsense, Einstein said. I could put a tiny measurement device with a spring on the slit and measure the recoil. That wouldn't do anything to the photon, so now we see an interference pattern and know where the photon went. Quantum physics is wrong. Well, Bohr said, but the recoil of the photon's too small to measure, so you can't distinguish before and after the recoil, and the interference pattern remains. And at the time, that was really all there was to say, because in reality, no one could measure the recoil of a single photon on a double slit until the guys from MIT did their experiment. In their experiment, the double slit isn't a double slit, but it's a grid that causes interference between photons. The grid they use is a cloud of atoms, about 30,000 lithium atoms if you want to know precisely. So if you're missing a few atoms now, you know where they went. These atoms are cooled to near absolute zero and trapped in a regular lattice with electromagnetic fields. They sit there much like, well, atoms in a lattice, but they're kept in place not by van der Waals forces like in crystals, and not because they're watching TikTok either, but by the electromagnetic fields in the trap. So unlike in crystals, you can turn off the trap. They then shine on the atom lattice with a laser in the red part of the visible spectrum, and they measure how the light scatters. If the atoms are neatly bound in their traps, you see the interference pattern. Then they turn off the trap so that the atoms are no longer bound to their location. What do you think will happen? If Einstein was right, then, in my interpretation, the answer would be nothing. One would still see the interference, because he thought that the interference would be there anyway. So, what do they see? In this figure, loosely speaking, the lower the point on the vertical axis, the more interference. If they turn off the trap, what happens is nothing. The interference is still there. At least initially, after turning off the trap, nothing happens. But then, if one waits for a while, the interference pattern does disappear. This is what they interpret as Einstein being wrong, because they say the reason that the interference pattern disappears is that when the atoms are no longer bound to their places, then their wave functions begin to run apart. Then the atoms can catch more information about where the photon was, and because of that, the interference disappears. So, Einstein was wrong because the experiment shows that the more you know about where the photon was, the less it interferes. It's a neat experiment and it gets a 0 out of 10 on my bullshit meter. However, I find the interpretation highly questionable. Because remember, they don't measure what the atoms do directly. They only measure what the photons do and infer from that what the atoms must have done. This means they use the disappearance of interference to conclude that the atoms, in some sense, measured where the photon was. It's not that I doubt it's correct, but it's a circular argument. It's logically wrong. And I think Einstein would have predicted that if one turns off the lattice, then the recoil on the atoms means that the lattice becomes increasingly less regular, and this is why the interference pattern vanishes. So was Einstein wrong or not? He both was and he wasn't. A lot of people asked me to comment on some papers that recently made headlines, according to which dark matter is evidence of a mirror universe, which could solve some problems. It's about 2 papers that were just published in PRD, one of the top journals in the foundations of physics. That sounds very interesting, so let's have a look. Before we talk about other universes, a big thank you to all our supporters, especially our patrons in Tier 4 and higher. This channel would not be possible without your help, and you too can help us on Patreon or by joining this channel right here on YouTube. Mirror universe is a catchy term, so much so that it's been used for 3 entirely different things. The first is a universe like our own, but going backward in time. In these theories, our universe didn't start from a big bang, but had a non-singular start at very low entropy. The entropy then increases away from that start in 2 directions, which is why time runs backwards in the other universe. You find this idea, for example, in Julian Barber's book Janus Point, but there are other versions of it with colliding brains or such. The second type of mirror universe is a universe like our own, but made of antimatter. This is often combined with the first version, but really they are 2 separate ideas. And then there is the mirror universe in which the standard model of particle physics is doubled in our universe, but we can't interact with the copy other than through gravity. So there are twice as many particles in the universe that we have detected. A mirror electron, a mirror up quark, a mirror photon. You get the idea. I think it's this latter universe with a copy of the standard model that the phrase in the press release refers to. Alas, if you look at the paper, the author merely uses a set of particles that have a vague resemblance to quarks in that they have the gauge group SUN. That's also where the similarities end, because while for quarks n equals 3, in the author's idea n is more like 100 or so. So he postulates that there are about 100 new particles that are related to each other and that can clump. The other sectors of the standard model don't appear in this theory. I wouldn't call that a mirror universe. It's like if I'd look into the mirror and see Taylor Swift. Nice, but not a good mirror. In any case, in his first paper, the author shows that one can arrange the properties of these particles so that they form black holes in the early universe. He then assumes that these black holes don't evaporate by Hawking radiation, but instead continue sitting around and that they make up dark matter. The evidence for this type of dark matter is entirely indirect and based on null results. That is, particle physicists' lack of success in measuring the particles in a detector. This bad mirror type of dark matter is a type of nightmare dark matter, more technically called gravitationally bound dark matter, which will never measure in a detector because it interacts too weakly. The second paper that's mentioned in the press release is actually about something entirely different. There, the author made up another way to produce particles that could make up dark matter, which is also why the image in the press release has nothing to do with mirror anything. I guess at this point you know what I'm going to say. These papers are a solid 10 out of 10 on my bullshit meter. 100 new particles, black hole, relic, dark matter, what? Excuse me? The reason I'm telling you about this is, well, for one thing, some of you asked, but also these papers got published in PRD, which used to be a good journal. They got published because this work checks all the boxes for what counts as good science in this area of physics now. Not only this, but the university also proudly put out a press release drawing attention to this nonsense. I could talk about nonsense publications of this sort every day, 10 times, and I still wouldn't run out of material. I don't do this because I'd go nuts and you'd get bored. Though if I went nuts, maybe you'd find that entertaining. In any case, I think on occasion I have to draw attention to it, just so you understand why I'm so distressed about what's going on in the foundations of physics, or not going on, as it were. Let me be clear that I don't blame the author of this paper or anyone else who publishes nonsense like this, because these are, for the most part, people who just do what they've been taught. And this is the real tragedy. This nonsense has become normal science. Or maybe I live in a mirror universe and this is why nothing makes sense to me? Hold on while I submit to PRD. David Deutsch is probably best known for his contributions to quantum computing, and each year I think he'll finally get his Nobel Prize. What's not so well known is that he's got his own theory of everything called Constructor theory. He and Chiara Maletto just published a paper in which they explain the origin of time. You can't blame them for a lack of ambition. Let's have a look. Time is a big headache for physicists. Despite thinking about it since probably the beginning of thinking, it's remained unclear what time really is, if anything. Many physicists believe now that time fundamentally doesn't exist at all, which makes a great excuse if you're late. Trust me, I'm a physicist. The new paper is an example of how a universe that fundamentally has no time can nevertheless give rise to a universe that has an emergent time, an apparent time that we use to keep track of change. You see, that's how modern physics works. First, we deny the existence of something, and then we explain where it came from. More seriously, the reason time is so difficult to make sense of is that it's deeply connected to the problem of quantum gravity. That's the missing unification of Einstein's theory of general relativity and quantum physics. Because these two theories treat time completely differently. In general relativity, time is a coordinate, and there are many different ways to choose it. There isn't just one time. There are infinitely many, just like there are infinitely many ways to put a coordinate grid on New York. That sounds confusing enough, but it gets worse if you add quantum physics to the picture. Because if space and time have quantum properties, then we can have several different times at once. If you don't know what it means to have several different times at once, don't worry. No one knows. That's the problem. So normally what one does in quantum gravity is to say, forget about all this, it doesn't mean anything, we'll bootstrap time from matter. That is, one uses the relative changes in matter configurations to construct something resembling a simple clock, for example, an oscillator, and then extract time from that. Okay, so that was the brief summary of how most physicists think about it. Deutsch and Maletto, however, have a very different approach to the laws of nature. Indeed, I must give credit to them for how audaciously they disregard the entire physics canon. If you like radical ideas, you'll love this one. It's like general relativity without the relativity and quantum physics without the quantum. Their idea is that the entire universe is ultimately explained by nothing more than transformations on physical systems. That is, ultimately what defines the universe is which changes are possible. They call those changes tasks. And the tasks are facilitated by, here it comes, constructors, hence the name constructor theory. The constructors ultimately determine what can happen in our universe. A simple example for a constructor could be a chemical catalyst that facilitates a reaction. Constructors basically make things happen, and for this they need to have a certain level of complexity. They can't be single particles. Constructor theory is therefore emphatically not a reductionist approach. Rather, the idea is that all the fundamental properties of nature are contained in the types of constructors that our universe can bring about. If that sounds weirdly backwards, that's the point. It's a completely different way to think about physics. In their new paper now, they formulate a way one can use constructors to, well, construct time. Your first idea might be to say, we'll use constructors that perform recurring tasks, because this is similar to an oscillation of sorts, and that's what one normally does to construct clocks. But this doesn't work because one can't know whether the recurrent task actually happens in the same time periods. It could just be getting slower and slower, like Windows updates. What they do instead is that they identify a shortest task, and that is doing nothing. It's when a constructor turns on and just turns off. They call this the null task. They take all these possible null tasks and group them together, and then they measure the changes in any system relative to these null tasks. This means one has now introduced a measure of change, which is time in some sense. Guys, I've spent 2 days trying to figure out how to explain this to you, but this is the best I could manage. It's really highly abstract. But I think that physics needs ideas like this that break out of the dominant framework of differential equations with initial conditions and so on. So I welcome the audacity. That said, honestly, the argument seems somewhat circular to me, because how can a task run if you don't have time already? But maybe my brain is just too small to comprehend this. On my bullshit meter, it's either a 0 or a 10, but I don't know which. I'm hoping constructor theory will eventually build me a better bullshit meter. And now, excuse me, I must attend to some null tasks. One of the biggest physics stories that's currently unfolding is that dark energy isn't constant. Just the other week, we talked about how this is now supported by multiple experiments, contrary to my expectations. As some of you noticed, I've been very vague with the implications for our understanding of the universe, because so far, we've just seen the data analyses. But this week, I came across a group of physicists who, stunningly enough, found that the data is neatly compatible with string theory. Yes, you heard that right. And they say the universe will recollapse, after which there could be another Big Bang. Let's have a look. Had you asked a string theorist in the 1980s what the cosmological constant is, I'm pretty sure they'd have said it's negative. This is because string theory really only works in universes with a negative cosmological constant. But then in the 1990s, observations showed that the cosmological constant is positive. Ever since, string theorists have tried to make their theory compatible with that, unsuccessfully. I've always wondered why they didn't just double down on it and insist that the cosmological constant is actually negative. Because personally, I've never found the evidence all that convincing. Yes, there was a Nobel Prize for it, but okay, maybe I should have been more convinced. In any case, things are changing. Up until a year ago, we thought dark energy behaves like this positive cosmological constant. That makes the expansion of the universe accelerate without end. Galaxies drift apart, stars run out of fuel, collapse to black holes, and the black holes evaporate in the unimaginably far future. The universe doesn't so much end as fade away towards a state of maximal entropy. It's called the heat death, because another way to say that entropy is maximal is that all free energy has been converted to heat. Alas, it'll be at temperatures near absolute zero. That's theoretical physics for you, where heat death happens at near absolute zero. But then in the past year, we've seen several different experiments finding that dark energy actually isn't constant, but it's getting weaker. The data come from the Dark Energy Survey, from the Dark Energy Spectroscopic Instrument DESI, and more recently also from the South Pole Telescope. The mismatch with a constant dark energy is currently somewhere in the range of 3 to 4 sigma. It's too early to say it's serious, but it's definitely curious. The Hubble tension started like this as well, and now it's at more than 6 sigma. But if dark energy is not a cosmological constant, then what is it? Well, if you need dark energy to change in time, you need some sort of field, and fields in physics are made of particles. That means we need some particles to do the job. One of the best motivated candidates are axions. They could also make up dark matter, which is an extra bonus, and they appear in almost every string model. Axions have very small masses, and this makes it difficult to detect them at particle colliders. They just go through the detector and disappear, leading to a tiny loss of energy that we wouldn't notice in the measurement uncertainty. The bottom line is that axions are compatible with everything we know. The authors of the new paper now show that a super light axion would have an almost constant energy density today, but one that changed in time just enough to fit the data. The most interesting thing about their theory, though, is not the axion itself. It's that the best fit to the data is a combination of the axion with a negative cosmological constant. What happens is that as the universe grows, the contribution from the axion dilutes, but the negative constant does not. Eventually, the negative constant begins to dominate. Then the expansion of the universe stalls and the recollapse begins. With the current best fit numbers, the turnaround would occur roughly 13 billion years from now, and the big crunch about 20 billion years later. That places the total lifetime of the universe at around 33 billion years, so by that reckoning we are already in the cosmic middle age. A negative cosmological constant also revives the dream of a cyclic universe with recurring big bangs. Various models for this have been proposed, from quantum gravity effects to collisions of higher dimensional branes. Every one of them first needs the universe to turn around, and that's exactly what a negative cosmological constant ensures. Collapse alone does not guarantee a bounce, but it makes one far more plausible. What are we to make of this? I give it a 6 out of 10 on the bullshit meter. This is because if you have more flexibility in your model, it's easier to fit more data, so that model is not so super convincing. However, it seems possible to me that eventually this model might come out to be simpler than having dark energy and dark matter be two separate things. So if these guys are right, then the universe will end in about 33 billion years. Just enough time to finally reply to that reviewer from 2009. Thanks for watching. See you tomorrow.